Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we are going to learn how to relate the standard cell potential to that of the change in standard Gibbs free energy. And so both the standard cell potential and the change in standard Gibbs free energy helps us predict the spontaneity of a chemical reaction based on this sign. And so if a reaction were to be spontaneous, and if we were to calculate their cell potential under standard conditions, for that oxidation reduction to be spontaneous, the sign for the standard cell potential should be positive. Now, according to thermodynamics, for the Gibbs free energy to represent a spontaneous reaction, the sign must be negative. And so the combination of a positive sign on the standard cell potential and a negative sign on the change in standard Gibbs free energy tells us that the oxidation reduction reaction is going to be spontaneous in a forward direction. So conversely, for the reaction to be non-spontaneous, the sign for the standard cell potential is going to have to be negative, and the sign for delta G will have to be positive. And so if you guys calculate a standard cell potential that is, for example, positive, and then you go through all of your calculations, all of your work, whatever, and you somehow calculated that the change in Gibbs free energy is positive, then you guys will have two conflicting signs such that your standard cell potential is telling you it's spontaneous, but delta G is telling you that it's going to be non-spontaneous if your calculated answer for delta G is positive. And so if you guys are getting conflicting directions in terms of the spontaneity of the chemical reaction, then you guys need to check your work, because that's an indication that there's some type of mistake that's been made, whether or not you guys did not incorporate your negative signs or something else. But long story short, the sign for the cell potential under standard conditions must be positive, and the delta G, the Gibbs free energy for that oxidation reduction reaction, will result into a negative sign for delta G. So both of these must be in line with each other. If they're not in line with each other, whether they're spontaneous or non-spontaneous, then there's something wrong in your calculations. That needs to be reviewed. All right. And so now that we've gone over the signs for what it means to be spontaneous under the standard cell potential and the change in Gibbs free energy, let's go ahead and talk about how the cell potential under standard conditions is or can be related to the change in Gibbs free energy. And so it turns out that in an electrical system, the maximum work is equal to the product of N, F, and the cell potential under standard conditions, where N represents the number of moles of electrons transferred, F represents Faraday's constant, and Faraday's constant is going to be 96,485 coulombs per mole of electron. Last but not least, the standard cell potential is going to be expressed in volts. And so looking at just the units for this equation, max work is equal to N, F, and E cell. So the unit for N is moles of electrons transferred. The unit for Faraday's constant is going to be coulombs per mole of electron transferred. And the unit for E cell is typically expressed in volts. So this is something that we've kind of looked at or calculated over and over again for the past 2 lecture videos. But when you guys are relating E cell and delta G, this volts needs to be converted into joules per coulomb. And so if you guys recall from the first lecture video that I've done for this specific chapter, 1 volt is equal to 1 joule per coulomb. And you want this form of, you want this unit to express the standard cell potential such that your units of coulombs can cancel out. And so if you multiply all 3 of these values, notice that your moles of electrons that's transferred is also canceled out. The only unit that you guys have remaining to express the unit for max work is joules. And so the unit for max work is going to be in joules. It can be also expressed in kilojoules, megajoules, millijoules, microjoules. The list continues. And so the main point is that you guys can add a prefix as needed to express joules under having different magnitudes and different values. Okay. And so let's see here. For us to complete the relationship between delta G and E cell, we have to take into consideration what sign delta G must be for it to be spontaneous. And so it turns out that a negative sign on delta G will represent a spontaneous reaction in the forward direction. Now, if that is equal to NFE, solving for delta G, I'm going to move that negative to the other side. In doing so, I will get this equation. And so if you wanted to express delta G and E cell under standard conditions, or if it was expressed in standard conditions, then you will just have to add the knots in the top right corner of delta G and E cell. All right. And so before I continue, I do want to mention very briefly that in the thermodynamics section, we discussed maximum work under pressure volume. However, since we're talking about work done by an electrical system, the maximum work, delta G, it's not going to be 0, right? And so if you guys recall from the past lecture video when I discussed this idea of reversible reactions and equilibrium, when delta G is equal to the equilibrium and all that stuff, that was for pressure volume work. And so since we're talking about an electrical system or electrical work, we're simply going to take the maximum work as delta G. Okay, so we're going to go ahead and use this equation to demonstrate how we can calculate for the change in Gibbs free energy for the following reaction. And once we have solved for the value of delta G, we're going to go ahead and take a look at the sign for delta G and E cell to make sure that the signs are parallel to each other, such that both perspectives, such that both points of view is giving us, one cohesive answer in regards to the spontaneity of a chemical reaction. All right. And so the first example that we're going to look at is this reaction system. And so here we have gold 3 plus reacting with aluminum solid to produce gold solid and aluminum ion. And so what we want to do is we want to determine the change in Gibbs free energy for the following for this reaction. And so I know that the change in Gibbs free energy under standard condition is equal to negative N times F times E cell, where F represents Faraday's constant, so that's 96,485 coulombs per mole of electron. Now, N is going to represent the number of electrons transferred during the course of the oxidation reduction reaction. And we can probably figure this out as we solve for the standard cell potential. And so notice that for this problem, I did not give you guys directly the standard reduction potential for each of these half reactions. And so what that's going to tell you is that you need to figure out what is oxidized, what's reduced, and then you need to use the standard reduction reference and find those values. Okay, and so we know that the standard cell potential can be calculated by taking the difference in the standard reduction potential minus that by the standard oxidation potential. But we just need to know if gold is going to be oxidized or if aluminum is going to be oxidized, or gold is going to be reduced and aluminum is going to be reduced. Once we figured out what's oxidized and reduced, and after we look up their standard reduction potential values using the reference sheet, then all you guys will need to do is just plug in those standard reduction potential values in their correct positions in this equation to figure out the standard cell potential. All right, so to determine what's oxidized and what's reduced, I need to list out my oxidation numbers. And so this is going to be +3. This is going to be 0, 0, and +3. And so I'm going to compare gold before and after the chemical reaction. And I'm going to compare the oxidation numbers for aluminum before and after the chemical reaction. So notice that my oxidation number for gold before the reaction is +3. Oxidation number after the reaction is 0. So that lets me know that reduction has occurred. In other words, gold 3 plus gained X amount of electrons. So overall, reduction is going to occur. So let's go ahead and take a look at aluminum. Before the reaction, oxidation number is 0. After the reaction, the value went up. And so that's going to represent oxidation. And so now that we know that gold 3 plus is going to be reduced, then all we have to do is look at our reference and find the reduction half reaction that would represent the gain of 3 electrons by the gold 3 ion. And so it kind of feels like we're searching for Waldo here, but I'm going to just highlight this. So it turns out that the standard reduction potential for the reduction of gold 3 ion to gold is going to be 1.50 volts. And so since gold 3 plus is undergoing reduction, then that means that I'm going to put 1.50 volts in the first part of this equation right here. And so that lets me know that aluminum 3 minus, well, let me take a step back. That lets me know that aluminum solid is undergoing oxidation. And so what I want to look for when I'm using this reference sheet is simply the reverse of what I'm seeing here, right? So instead of looking at it this way, when I'm looking for my standard reduction potential in my reference chart, I'm going to look at it this way. So I'm going to search for aluminum 3 plus. And so it looks like aluminum 3 plus is going to be negative 1.66. Now, please remember that these are standard reduction potentials, reduction specifically. And so since these are standard reduction potentials, then we're going to go ahead and plug in the negative 1.66 into the place where oxidation is being described in the equation, right? Because remember, aluminum is undergoing oxidation. So therefore, that negative 1.66 needs to be plugged in into the equation after the minus sign. So there's going to be minus negative 1.66 volts. So please don't forget this negative. This negative here will convert this standard reduction potential into the standard oxidation potential. All right, so adding through, we're going to take 1.50 and we're going to add that by 1.66. And the reason why I say add is because a negative times a negative is a positive. And so overall, your standard cell potential is going to be 3.16 volts. And so we've now figured out that this is going to be 3.16 volts. Now remember, since we need to find delta G, we need to change the units from volts to joules per coulomb, so that the coulomb can cancel each other out. And so the last thing that we need to figure out is the value for N. So N represents the number of moles of electrons that's being transferred. And so for this very simple chemical reaction, we can go ahead and figure out that the number of moles of electrons that's transferred was 3. And so how did I figure that out? Well, you guys can write out the half reactions, but since the half reactions are already written out for me, I'm just going to go ahead and use this. Oh no. So if you look, gold must gain 3 electrons. And here in this case, if we're looking at the reduction of aluminum 3 plus, that aluminum is also going to have to gain 3 electrons. And so it looks like 3 electrons is the common denominator. But just to show my work, I'm going to quickly write this out. And so for gold, for it to undergo reduction, it must gain an electron. And so gold will have to gain 3 electrons for the positive 3 to cancel out so that it can be 0. Okay, and so this is describing my reduction half reaction. Now if I'm looking at oxidation with aluminum, oxidation means losing electrons. And so here my aluminum solid, maybe I'll just move this over, is going to undergo oxidation, meaning I'm going to lose electrons. And since my final product was aluminum 3 plus, then that tells me that for aluminum to get that 3 positive charge, it must lose 3 electrons. Now if you guys add these two equations, we know that these 3 electrons and these 3 electrons are going to cancel, leaving us with just Au3 plus Al solid to produce Au solid plus Al3 plus. Okay. And so I'm not really concerned about my resulting equation when I add them because, it's just this, right? So if I kind of zoom out, notice that both of my answers are the same. So that lets me know that I added these two half reactions correctly. What I do want to figure out is just simply the number of electrons transferred between this oxidation and reduction reaction. And so it looks like I have 3 moles of electrons that's transferred. So now that I have all of my pieces, I'm just simply going to clean up my work. So I'm just going to go ahead and copy this real quick. So that I have delta G under standard conditions is going to equal to negative 3 moles of electron times this by 96,485 Coulomb per mole of electron. And so this needs to be multiplied by 3.16 joules per Coulomb. And so I can go ahead and cancel my moles of electrons. My coulombs will cancel. And when I multiply my values, so I will get 3.16 times this by 96,485 times this by negative 3. And that's going to give me negative 9.15. And so this 3 is an exact number. So when it comes to sig figs, you are not going to report 1 as your lowest sig fig because we transferred exactly 3 moles of electrons. It's a discrete object. And so really, the 3 is coming from your E cell. So overall, I have negative 9.15 times 10 to the positive 5 joules. And so once again, if I wanted to express this in kilojoules, I can break that positive 5, that times 10 to the positive 5 into 2 pieces. Times 10 to the positive 3, and times 10 to the positive 2 joules. And so this positive 3 is going to be a kilo, And so I can go ahead and express positive 2 by moving this decimal place 1, 2, 2 places to the right. And so overall, I would have negative 915 kilojoules. And that would be my value for the change in Gibbs free energy under standard conditions. So let's go ahead and check out the sign. Notice that my sign is negative. So this is telling me, according to thermodynamics, this is telling me that the reaction is spontaneous in the forward direction. And so I want you guys to look at the value or the sign of E cell. The value of your cell potential is going to be 3.16, more specifically positive 3.16. And if you guys have a positive value, that means that this reaction is also spontaneous. Okay. And so we have a positive sign here, and we have a negative sign here, and both perspectives or both points of view is telling us that, yeah, the forward reaction will definitely be spontaneous. Okay. Now, if you guys got a positive value here and a positive value here, you guys will have two conflicting results, right? This positive delta G is telling you that the reaction is non-spontaneous, but a positive value for E cell is telling you that the reaction is spontaneous. So that can never occur. Okay. So you always want to check your signs to make sure that they're pointing in the same direction. All right, so now that we've kind of dipped our toes in using this equation, we're going to go ahead and do it again for this chemical reaction. And so here in this case, we're going to calculate the Gibbs free energy for this specific reaction. And for us to do so, we're going to go ahead and use this equation. And we need to figure out what E cell is, and we need to figure out N. We already know Faraday's constant. That's going to be 96,485 coulombs per mole of electrons transferred. And so to calculate the standard cell potential, that's going to equal to the reduction potential minus the potential for oxidation. Very similar to what we did in the previous problem. We need to identify if magnesium is undergoing oxidation or reduction, or if it's lead that's undergoing oxidation or reduction. And so to do so, we need to figure out our oxidation numbers. So this is going to be 0, plus 2, plus 2, and 0. And so I'm going to go ahead and compare my magnesiums before and after the reaction, specifically the oxidation numbers. And notice that it's going from 0 to positive 2. So since my oxidation numbers are going up, this is going to be oxidation. Comparing my numbers here between lead, I'm going from plus 2 to 0. And so since I'm going from plus 2 to 0, then lead 2 is undergoing reduction. So I'm going to go ahead and summarize my half reactions so that I know how many electrons are being transferred. And so for the oxidation half reaction, remember oxidation means losing electrons. So whenever you're losing electrons, those electrons are going to be found on the right side of the arrow. So here we have magnesium, solid. We're going to undergo oxidation, and that will produce magnesium 2 plus, as indicated here. And the only way to get a positive 2 is if we lose 2 electrons. Now looking at reduction, reduction means to gain electrons. And so if we have lead 2 plus, and for it to become lead solid with no charge, as indicated here, that means that we would have to add 2 electrons to balance the charges out. And so this is going to be reduction. And so if we were to add both of these equations, and I'm not going to add these equations all the way through because the result is going to be this equation right here. But, you know, it never hurts for you to add those equations, especially if they're a little bit more complex. And we'll see that in the next lecture video. But for now, we're just doing baby steps here. So notice that there's 2 electrons on the left-hand side, 2 electrons on the right-hand side. And so the number of moles of electrons that's transferred during the course of this reaction is 2. So this is going to be 2 moles of electrons. So the last thing I need to figure out is my standard cell potential. So my reduction is happening with lead. So I'm going to look at my reference chart, and I automatically found that the reduction potential for 2 electrons to go to lead 2 ion is negative 0.13. And so since lead is undergoing reduction, then the value here is going to be negative 0.13. Okay. And so looking back at this equation, magnesium is undergoing oxidation. And so when you guys are trying to look for magnesium in your standard reduction potential reference chart, you want to look backwards. And so it's Mg2 plus that's becoming Mg. So if you look at it backwards, you'll be able to find it in your standard reduction potential. If you guys look forward, in the forward direction, you guys won't find it in your standard reduction potential. Why? Because everything here is describing reduction, not oxidation. All right, so looking for magnesium, in which there's 2 electrons transferred, looks like that value is negative 2.37. And so I'm going to go ahead and plug in negative 2.37 in place of the standard cell potential for oxidation. Because oxidation, so it's magnesium that's undergoing oxidation. And so the last thing I need to do is carry down that negative sign. So negative times negative is positive. So what I'm doing is I'm adding both of these together. So the standard cell potential is just going to be 2.37 minus that by 0.13. And I say minus 0.13 because this guy is negative. And so overall, I get positive 2.24 volts, or 2.24 joules per coulomb. All right, so now that I have all of my pieces, I'm just going to go ahead and calculate delta G naught. And so this is going to be negative 2 moles of electron times this by Faraday's constant, 96,485 coulombs per mole of electron. So these guys will cancel. And then times this by 2.24 joules per coulomb. Coulombs will cancel. So if I multiply all of them together, I'm going to get a delta G value that's going to be negative 4.32 times 10 to the positive 5. And this is going to be joules, because this is the only unit that's remaining. And so I'm going to go ahead and break down the times 10 to the positive 5 to two items, times 10 to the positive 2, times 10 to the positive 3. And so I know that this is a kilo. And then this times 10 to the positive 2 lets me know that I can move this decimal place 2 places to the right. And so my final answer is going to be negative 432 kilojoules. Okay. Once again, looking at my sign, this is telling me that my reaction is spontaneous because the sign of the Gibbs free energy is negative. And it parallels to the story that the standard cell potential is telling me. Remember, if the standard cell potential is positive, then that's letting us know that the oxidation reduction reaction is spontaneous in the forward direction. And so basically, since both signs are telling me the same story, then, in terms of the signs themselves, like I've done the calculation correctly. The only way that you guys can get this wrong is if your number is wrong, right? And so just go ahead and make sure to check your work. All right, so the last example that I want to talk about is, it's not written, so I'll just go ahead and write it here. Let me zoom in. And so here we have 2 Au solid plus 3 calcium 2 plus aqueous to produce 2 Au 3 plus aqueous plus 3 calcium solid. So same idea. We're going to go ahead and try to figure out the change in standard Gibbs free energy. And so for us to do so, we're going to go ahead and use this equation. And so the first thing that I need to do is figure out what's oxidized and what's reduced. And so according to my oxidation numbers, this is 0, this is +2, this is +3, and this is 0. Now I'm going to write the oxidation numbers in a different color. So this is going to be 0, +2, +3, and 0. And so according to my oxidation numbers for gold, notice that my oxidation number is increasing from left to right. And so that's telling me that gold is undergoing oxidation. And if I were to look at my calcium, my oxidation number is decreasing from left to right. So my calcium is undergoing reduction. And so I can go ahead and write half reactions. And so for now, I'm just going to ignore all of this stuff, right? So don't worry about this stuff for now. And so when I'm writing my half reactions for, let's just say, oxidation of gold, I'm going to have Au solid. So this is undergoing oxidation. And that's going to produce Au3 plus. And that's going to be aqueous. And so since I'm losing electrons, for me to get positive 3, I have to lose 3 electrons. And so for calcium that's undergoing reduction, I'm going to have calcium 2 plus, and for it to undergo reduction, it needs to gain electrons. So therefore, those electrons are going to be found on the left side of the equation. And so to balance out the charge, I need to gain 2 electrons. Okay, and so if you guys look at the number of electrons that's being transferred, they're actually not the same between oxidation and reduction. And so you can't just have 3 electrons and then only gain 2 of it. And so whatever is lost must also be gained in the same proportion. And so for us to make sure that the number of electrons are the same, we would have to manipulate this equation. And so the common multiple between 3 and 2 is 6. And so therefore we need to multiply this by 2, and we need to multiply all of this by 3. And so what we get, and when we multiply this, we have to distribute to everything. So what we get at the top, oops, what's happening? It's going to be 2 Au solid to produce 2 Au gold, or Au is gold actually. So, so 2 moles of solid gold to produce 2 moles of aqueous gold, and that's going to give us 6 electrons. And then for the reduction, it's going to be 3 moles of calcium ion plus 6 moles of electron to produce 3 moles of solid calcium. Now, when we add both of these equations, notice that your 6 electrons are going to cancel because they're found on opposite sides of the equation. So this is going to give us 2 Au solid plus 3 Ca2 plus to produce 2 Au3 plus and 3 calcium solid. So this final equation that I wrote is pretty much the original equation that I wrote up here. Oh no. Okay. So I'm going to kind of zoom out real quick so that way you guys can see it. And so this equation is the same as my original equation. And for those two equations to match, I had to transfer 6 electrons. And so my work tells me that the value of N is equal to 6 moles of electron. Okay. So for some more complex chemical reactions, you guys will have to do a little bit more work to figure out N. And so for the previous two reactions, it just turns out that the moles of electrons are the same, so we didn't really have to do anything else. Okay. All right, so now that we've figured out N, we know what F is. We just need to figure out the change in cell potential. I'm sorry, that we're just going to have to figure out the standard cell potential. So I'll just go ahead and write it down here. So the standard cell potential is equal to the difference between reduction and oxidation. It's the difference of their potentials. So looking at my work, notice that calcium is undergoing reduction. And so I just need to find calcium. Okay, so it looks like calcium is down here. So it's negative 2.76. And so since calcium is undergoing reduction, it's going to be negative 2.76 volts minus oxidation. And so notice that gold is undergoing oxidation. So we just need to find where gold is, and specifically gold that's transferring 3 electrons. And so that value is right here, 1.50. It's going to be positive 1.50 volts. Just to check that. So notice how this is going to be a positive value. All right, so if we plug this into the calculator, we get so 2.76 minus 0.5. So what we get is negative 4.26 volts, or negative 4.26 joules per coulomb. And so since the sign for the standard cell potential is negative, we already know that this reaction is going to be non-spontaneous. And so we should expect that the value of our delta G will be positive. Positive delta G will reflect a non-spontaneous reaction as well. All right, and so if this is negative 4.26, I'm just going to erase this right here. I'm running out of room. So this is going to be 96,485. And then this is going to be 6. Okay. So I know that my final answer, my final unit is going to be kilojoules. And so I'm not, for this example, I'm not going to write out my units just because I'm running out of room. And so I'm going to multiply all of these. So I want you guys to notice that there's a negative times this by a negative. So overall, my answer is going to be positive. So delta G, when I plug it into my calculator, I get 2.46 times 10 to the positive 6 joules. And so if I extract a positive 3 out, then I get delta G is equal to 2.46 times 10 to the positive 3 kilojoules. And if I wanted to, I can express this scientific notation as an actual value. And so this is going to be positive 2,460 kilojoules. And so this is going to be my final answer. Actually, both of these can work as your final answer. And so notice that the sign is positive. So this is telling us that the reaction is also non-spontaneous if the value of delta G is positive. And so it looks like our signs for E cell and delta G are in agreement. They both conclude that this reaction is non-spontaneous in the forward direction. And so what that means is that the reverse reaction is spontaneous. Cool. So that's pretty much it for this lecture video.